ETS Lindgren is a leading manufacturer of antennas and other equipment for electromagnetic compatibility or EMC testing. EMC testing is used to validate that the electromagnetic emissions from an electronic device comply with federal regulations. EMC tests to check emissions at frequencies above 1 GHz require an antenna to maintain its aim at the device under test, or DUT, as the antenna raises in elevation from 1 meter to 4 meters. ETS Lindgren currently offers an antenna tower, which rotates the antenna as it raises via a mechanical system. Links for this system are changed to switch between DUT distances of 3 meters, 5 meters, and 10 meters from the tower. To expand the automatic bore sighting capability of their equipment lineup, Director Zhong Chen at ETS Lindgren enlisted the help of Senior Project Team 5 at Grand Valley State University, consisting of Captain Nicholas Mullenhouse, Sponsor Point of Contact Timothy Tobias, Faculty Point of Contact Harris Spungen, and Secretary Grant Lubert.
The new device had to be an add-on, interfacing between the existing tower and antenna, and it had to be able to support an antenna up to 15 pounds and 1.3 feet long.
For proper antenna reception, the device had to maintain the aim of the antenna within 2 degrees of the center of the DUT. The device also had to minimize adding electromagnetic noise, so dielectric materials were to be used wherever practical.
Here's our device, which sits on the boom, replacing the original location of the antenna. Here's our drive shaft, which rotates the antenna, connected to the pneumatic stepper motor. As you can see here, the air lines lead into the motor and are connected at the bottom where the console sits. The console contains the electronics and the valves, and on the front of the console you can cycle through our 9 profiles, which allow us to efficiently and quickly do EMC testing.
The Boresight device can be broken up into 4 sub-assemblies: the input boom, the output boom, the device frame, and the drivetrain.
The input boom attaches to the boom coming off the tower where the antenna attaches. It simply slides onto the boom and secures with the hand knobs as before.
The output boom is the attachment point for the antenna, and it's rotated by the drive shaft. Hand knobs are used once again for securing the antenna. The device frame holds the other sub-assemblies together. To minimize added electromagnetic noise, the frame is composed primarily of Delrin. Ceramic ball bearings and glass-filled and peak fasteners are also used for this reason.
The drivetrain consists of the pneumatic stepper motor driving a set of timing belt pulleys and ultimately the drive shaft. The timing pulleys we selected increase both the torque and the stepping resolution of the motor threefold.
Pneumatics, electronics, and user input come together at the console. The heart of the console is a set of 3 3-tube valves, controlled by a Texas Instruments microcontroller. Since the valves are inductive loads, the console was designed to be kept far from the antenna while still being user-friendly. The aluminum case also helps to shield the electronics from adding electromagnetic noise to the testing chamber. The right side of the console contains a barrel jack for connecting the power supply, the input fitting for the compressed air from the shop or other source, the air regulator, and the exhaust port with muffler. The left side of the console contains an M12 8-pin female connector for the draw wire sensor. This sensor detects the height of the antenna and tells the microcontroller where to rotate the antenna. Atop the console are the outlet fittings for the 3 valves. Inside the console, the electronics are powered by a 24-volt DC 6-amp power supply, which connects to the barrel jack shown previously. The 24 volts matches the rating of the solenoid valves and must be stepped down to 5 volts for the microcontroller and peripherals. The valves, manifold, microcontroller, and transistor board mount to the steel panel fastened to the inside back wall of the console. We're using quick connect elbow fittings for all the valves and manifolds for easy plumbing. The air comes in through the air in port to the regulator, reducing the pressure to 80 psi to each of the valves via the intake manifold. Opening a valve while the rest are closed rotates the antenna by 1 degree. The direction of that rotation is given by the sequence of the opening of the valves. Reversing this sequence also reverses the rotation direction. The front of the console has the user interface. Power switch is down here in the lower right corner. The test profile selected is shown on this 7-segment LED, and the settings for that profile are shown on the LCD here. Toggle profiles with the up and down buttons here. To edit the selected profile, hit the Edit Profile button. Then use the left and right buttons to move the cursor to the desired digit for the DUT distance, DUT height, or antenna length. Once the cursor is at the digit, enter the new digit with the keypad. When finished, hit the Save key, or hit Cancel to restore the previous settings. The console features the calibration mode for calibrating the draw wire sensor for consistent bore sighting on any tower. Simply toggle beyond the final profile to reach it. There's also an adjust mode, which manually adjusts the antenna angle.
The biggest obstacle we had to overcome during the design was precisely controlling the antenna rotation without using changing electric current. This meant electric motors were not an option. Pneumatic actuators, which don't use electricity, lacked the precision we needed for the antenna angle. We eventually discovered the pneumatic stepper motor that, while eating up a sizable portion of our budget, provided the precision we needed without using electric current. It's a new technology, and we hope through this project that it may be used more throughout the world.
The biggest obstacle we had during the build phase was getting our draw wire sensor to work. We had to add an extra subcircuit just for the transceiver during assembly. Plus, during testing, we accidentally fried 2 microcontrollers and 3 transceivers with our benchtop power supply. The high cost of this sensor made us even more careful during testing. We ultimately were able to get it working with some rewiring and by delaying the initial sensor readings, which allowed our sensor to reach its proper voltage before using it. Here is a test of our device. We are secured on the boom of the tower, and a laser pointer is secured to the output boom of our device. All of the air lines and power are connected, so let's apply some pressure. We want to bring this to about 75 psi. That should be good. Now let's turn on the console. We are not properly aimed at the center of the target, so let's go to adjust mode. Here, we can manually control where the antenna aims at. Now we are perfectly aligned. Let's go to one of our profiles for conducting a test. We have 9 different profiles, but we are just going to go to profile 1. All set, let's start our test. As the antenna raises, the laser stays at a fixed point in space. This shows that our bore sighting is accurate. Test successful.